Okay, hello everyone. Welcome back to the afternoon session. The next speaker is Zhao. Ye is an assistant professor at Georgia Tech. He is doing very cool research in planning, control, decision-making, optimization, and learning for robotic systems. Yeah, stage is yours. We are very much looking forward to your talk.
All right. Yeah, thanks, Majid, for the nice introduction. And so hello, everyone. I'm Zhao from Georgia Tech. And so first, I want to thank the organizers for organizing this wonderful workshop. And I actually attend some of the morning presentations and panels. It's very excellent. And I really hope I can be there and join in person. So today I'm going to talk about something I think a little bit different from the morning sections, and especially about this high-level decision-making algorithms and trajectory optimization, and how to explore and discover these principled architectures for these hierarchical planning and optimization algorithms. And the students I think shown on this page are literally that all the works, and I think they deserve all the credits. So I think at the very beginning, I want to give just a very high-level overview about some directions we have been exploring. And at Georgia Tech, I direct the laboratory for intelligent decision on the autonomous robots. And we have been looking at especially task and motion planning algorithms, decision-making algorithms for highly dynamic locomotion and manipulation. And we are especially interested in trajectory optimization, symbolic planning algorithms where we can reason about or even provide formal guarantees. So from a very high-level perspective, a fundamental question we are interested in is what types of planning and decision-making algorithms do this locomotion and manipulation system need to achieve very agile, robust, collaborative, and safe behaviors, especially through contact, so through physical interactions. And in this talk, I think I will particularly address two questions about the hierarchical task and motion planning structure and distributed trajectory optimization. So the first question is about how can we design the hierarchical task and motion planning structure to better reason about robustness and failure recovery. So I think many times there's a formal guarantee such as a safety or probable correctness is only reasons at a very specific layer and cannot be guaranteed to either higher or maybe lower layers. So in this case, how can we design more resilient and robust mechanisms to enhance the overall safety and the task success rate for this hierarchical planning framework, or if we cannot really provide like 100% safety or even improve it. And then the second question on the trajectory optimization side, so I will talk about some of our recent distributed trajectory optimization work to achieve dynamic consensus, especially for this large-scale nonlinear program, and talk about its capabilities and the limits. So I hope at the end of this talk, I can really convince you these are the two important questions we should really put our effort on. And if not, I think I'll go back and maybe further improve my work and my presentation skills to make it better delivered. Okay, so I would like to first highlight some of our recent works. Well, I think over the past few years, and since 2016, we have been looking at this unified locomotion and manipulation problems from task and motion planning perspective. And we formulate the whole body locomotion planning problem as a two-player game between the robots and the interacted environments. And here the environments could be adversarial. For example, it can include like very bad situations like the train get crashed, or maybe a human appears in the scene, or if there's like maybe a very narrow passage for the robot to maneuver. And the goal here is to synthesize a winning strategy such that the robots can win the game, basically maneuver this very adversarial environments successfully. And we designed the so-called temporal logic-based reactive planners to make decisions on the robot's contact sequence. So to achieve this dynamic maneuvering, I think a key question is how to intelligently compose and decompose these very complex motions. And this motivated us to investigate this template-based agile locomotion method. And we refer a lot to human motions, especially those seen in parkour or gymnastics. And then we extract these essential dynamics and model the abstract behaviors. And I think, as many of us know, in the field of dynamic locomotion, many groups use these simplified models for planning and control. For instance, inverted pendulum model, hopping model, multi-contact model, etc. And here, our goal is to unify these template models using sequential composition approach for planning. And it is essential to understand how to intelligently switch among different locomotion modes in response to environmental events. And since then, since I started at Georgia Tech, we have been exploring these temporal logic-based task planning and allocation problems for like navigation in the real-world environment from multiple angles, so including navigation in complex environments, heterogeneous robot teaming, and task allocation, reallocation, and how to let like a walking robot team up with a drone system to resolve some environmental conflict at runtime through some like online planning and online resynthesis method. And into this talk, I will not talk about navigation problems. So instead, I'm going to talk about one specific problem, especially on push recovery, and how to design agile and robust motions using our task motion planning framework. And as many of us know, this push recovery problem has been a like long-standing topic in the dynamic locomotion community. There has been like many related works such as like capture points, MPC approach based foot placement planning, or different kind of recovery strategies. However, I think many times the perturbation applied in the experiments is very simple, empirical, and I think a very systematic study of the perturbation applied phases, directions, the magnitude is significant to design practically useful recovery strategies. But I think this is still underexplored. And also the leg crossing behavior, I think, have been largely ignored, I think, especially due to the potential self-collision between two legs. So in this work, we study how to design agile locomotion plans that could be resilient to perturbations happens at any time. And I want to emphasize that this leg crossing behavior is actually essential, I think, not only for the perturbation cases, but also for other real world scenarios. For example, think about like a human walk across a river and put its foot locations on this zigzag stepping stone. And this, in certain situations, it has to like initiate these leg crossing behaviors to make sure it will step on the right locations. And literally to avoid this like collisions, I think the traditional reduced order model might not be enough. So we really have to think about the full body kinematics and dynamics and design the full body planning strategy to avoid this self-like collision. And especially at the higher level, basically to make the foot placement decisions, we use our fit-space planner that's actually reasoning about the robot center of mass dynamics in the state space. And we have a series of previous work on this, but here I just want to briefly highlight. So this approach actually designed these Riemannian cells to quantify the robust margins in the center of mass state space. And these Riemannian cells are actually computed using the locomotion manifolds analytical solutions based on the reduced order model, which can give us like very nice closed form solutions. And then using this high-level temporal logic-based method, we can sequentially compose and build dynamic transitions across keyframe states during multiple walking steps. And I think I would like to maybe just use one slide to give a like very high-level idea about the linear temporal logic. I think although this is a topic maybe many people in the room are not very familiar with, but I think it makes sense to share some like high-level ideas and I think the core part of our algorithm. And this LTL approach, you can think is basically a formal language of rules and symbolisms to express and reason about like system properties in terms of time. And using this approach, we can synthesize a reactive decision maker and formulates this whole problem as a two-player game between the robot and the environments. So you can think these two players that kind of interact in a turn-based game and kind of play a chess all together. And by following the syntax and semantics of LTL method, we can actually specify a series of task specifications we want to achieve. And here I just want to give one example, like especially in this push recovery problem, let's say we want the robot to achieve the recovery behavior within 2 walking steps. And we can actually specify it as a temporal logic specification, like say on the top left is say like it is always true that when the keyframe K is not in the steady states, then in the next walking step, the keyframe or the next walking step keyframe is going to recover back to the steady state KSS. And this circle operator represents next, and the square, the box operator represent always. So this is just one example, and actually we can use these rules and symbolisms to define a set of specifications we want to achieve for the system. And then by leveraging some of the shelf solvers, we can synthesize these decision makers for the keyframe states offline. And then in the online execution, when we detect the current keyframe states in these Riemannian cells, we can make the decisions of the next walking steps. So this is the kind of how this LTL reactive synthesis works. And then overall, we have this hierarchically integrated task and motion planners. And as I mentioned, we symbolically parameterize the environment perturbations exerted from this treadmill. And so these perturbations basically try to falsify the robot decisions, which is actually the foot locations and the center of mass keyframe states like the apex velocity. And here, this high-level temporal logic-based formal method actually synthesize robot decisions to make sure the robots can always recover from these perturbations. But this reactive synthesis only happens at the discrete apex keyframe state. And then you may ask, okay, how we can really handle perturbations that doesn't not occur at the apex states like at any other continuous phases. So to address this, we design a middle layer behavior tree execution layer to make these online modifications to address perturbations that can actually happen at any continuous locomotion phases. And then this updated action plan is sent to the underlying trajectory optimization for full body trajectory generation. And overall, this hierarchical task motion planning framework, we have this multiple robust mechanisms to address, to handle the environmental perturbations. So we tested our hierarchical planning algorithms on this Karen system, which has actually mainly designed for clinical and rehabilitation studies. I think one of the morning section speakers kind of mentioned this platform when the panel discussed this visual perception topic. But in this study, we haven't really used this curved screen for virtual reality. We are mainly stay on the mechanical side. So this Vertex treadmill on the dome can actually apply any directional perturbations at any specific time. And I think this is a very nice platform for us to study push recovery in a very systematic way. And here we show like case studies for 4 different directional perturbations. And you can see the first like 0-degree perturbation actually initiates these leg crossing behaviors. And we also have this systematic studies on omnidirectional perturbations that can be applied at different locomotion phases. And this spider chart sort of show the maximum tolerable perturbations the robot can sustain. I mean, especially for chassis robots. And the graph is asymmetric, and I think this is primarily due to the more constrained kinematics workspace of the swing legs during this cross leg scenario. So I think this work really motivates us to think about I think a few more directions I think we are really interested in, and especially how to design more robust strategies by exploring different system architecture properties when we have this hierarchical planning framework. And especially in certain situations, these high-level LTL specifications command can actually not be successfully executed by the underlying trajectory optimization because very complicated physics constraint at the low level. And in this case, I think we might leverage the feasibility of this trajectory optimization result to refine the task specifications at a higher level and enable higher success rate overall. And you can think sort of they have like this bottom-up feedback loops in this whole framework. And also at the temporologic level, exploring more advanced method that can reason about like robust semantics and probabilistic satisfactions give us the opportunity to quantify locomotion uncertainties in a more formal way. But I think the question is how we can scale this formal method to like higher dimensional robotic systems like the system thinks many of this the so-called signal temporal logic approach actually solve mixed integer programs type of problem. And also, I think when we have like multiple like task specifications we want to achieve, sometimes there could be some specifications that could be like a self-contradictory, or maybe certain specifications can really not be achieved because the environmental constraints. So in this case, how we can leverage like machine learning algorithms to generate policies that can actually satisfy the task specifications as much as it can, but also allow some specification violations to certain levels. I think these are all interesting questions. I think we don't know the exact answer yet, but we would like to explore in the near future. So I think I would like to give maybe a stop here and before moving forward, if any questions. So the second part is a little bit different from the first part. So just make sure there's no questions from the audience. If they're good, I will continue. Maybe we can leave all to the end. Okay, cool. So so now let's switch the gear maybe to the low-level problems, the trajectory optimization, and how can we decompose the holistic trajectory optimization problems into maybe multiple sub-problems and then achieve dynamic consensus. So I think there has been a large body of works using these single rigid body models, or maybe extensions using like machine learning approach to learn these time varying momentum inertias, or maybe assume like each leg have like kind of a point mass. It is sort of like somewhere middle ground between the single rigid body model and the full body robotic models. And on the other hand, there are quite a few research groups like decomposing the trajectory optimizations into like maybe 2 or maybe more blocks and alternate between this centroidal momentum blocks and the kinematics or dynamics blocks to achieve dynamic consensus, which actually show great promise to solve more complex trajectory optimization problems. However, I think there are still like no like alternating optimization frameworks that currently can like both optimize the contact sequence and use this inertial aware reduced order model at the centroidal level, and at the same time formulates these constraint full body dynamics at the whole body level. So in this work, we propose a alternating direction method for offline trajectory generation to achieve dynamic consensus between centroidal and whole body dynamics, and also a convex MPC with full centroidal dynamics for this online tracking. And this is actually led by my students, Z, Nathan, and also Bruce from Hutchinson's lab. So, so today I will only talk about this trajectory optimization part and discuss the distributed optimization structure design. So in general, I think many of us know, like when we solve this large-scale constraint trajectory optimization problem involving both centroidal and whole body dynamics, there's really a long list of inequality constraints to be handled. And I mean, if you take a look at this problem, you can see like how complex the formulation is and how many numerical problems we have to handle from a holistic perspective. And we certainly need to think about how, if there's any like internal structures we can leverage in a principled way, or maybe decompose the problem in a distributed fashion. And here's this our proposed alternating direction structure. So overall, the centroidal and whole body optimization is solved alternatively until dynamic consensus. And especially for the centroidal optimization part, instead of using this single rigid body models, we use a centroidal dynamics model with this equi-momental ellipsoid representation, including this ellipsoid size and orientation, and it's donated as this inertial tensor I ellipse. And this equi-momental term basically means there exists an ellipsoid that's actually has equivalent moment of inertia to this composite rigid body moment of inertia represented that by this ICRB, actually calculated from the whole body optimization, which I will talk about in a second. And basically to enforce this equi-momental features, we can add a cost term to track the reference composite rigid body moment of inertia as shown in this red box. And the nice thing is that now this centroidal ellipsoid actually gets rid of these direct dependencies on the full body joint states, but at the same time, it sort of like indirectly incorporates the whole body informations through this composite rigid body moment of inertia, this ICRB. And you can think this centroidal momentum ellipsoid is a kind of a more advanced version of the single rigid body model, but without any like model simplifications. And in the meanwhile, this ellipsoid mass constraints has to be enforced to make sure that the robot mass is always remain the same. And we have additional equality and inequality constraints, and we can solve this using the direct method. In this case, we use the IP-opts. And then now let's take a look at the whole body optimization, which incorporates the whole body dynamics model, but actually with minimal additional constraints, just including the joint torque limits and frictional cone constraints. So it doesn't need to worry about the center of mass reference trajectories, centroidal momentum, or the foot locations, which are actually already offloaded to the centroidal momentum optimization block. So overall, we can solve this problem in a kind of iterative way and until the dynamic consensus. So we evaluate these algorithms both on mini-cheetah and the A1 robots. So as we can see, this method can really generate dynamic locomotion gates, such as like catering. If we give some like motion capture data as a high-level goal input, and can also achieve this highly dynamic parkour kind of maneuver with this long aerial faces. And this example is interesting. So to literally differentiate from this single rigid body model or the traditional centroidal momentum models that heavily rely on the ground reaction forces, we studied this zero gravity body reorientation problem, which is actually called inertial shaping. So think in this case, since there's no gravity, no like external contact are presented in this problem, this robot is really forced to just rely on its robot's lean motions and to produce like the turning behaviors. And this robot starts with this static initial configuration, and its goal is to turn its trunk by 90 degrees, like in 2 seconds. And I think this type of motions is actually not really achievable by the traditional single rigid body model or the standard centroidal dynamics model. And we also benchmark the performance with respect to a single rigid body model with the full body inverse kinematics baseline approach. And actually both methods can generate this desired 180-degree maneuvers as shown in this visualization. But however, actually by achieving this consensus through centroidal inertial feedback from the whole body optimization, like our method can leverage additional lag movements during the takeoff phase, which actually lead to a larger centroidal angular momentum. And this larger angular momentum actually induce a very special rotation motion that's actually play a very key role in this successfully implementation on the hardware. I will show exactly next. So we tested this on our hardware and using the exact same low-level controller to track the motion. And the trajectories actually generates from the single rigid body models plus this inverse kinematics actually failed to get the robot to achieve this 180-degree rotation. And if you look at closely the motion using our method, the robot have a swift counter rotation at the very beginning. And this slight but non-trivial change of angular momentum actually guarantee a high fidelity momentum trajectory to be tracked by our controller and achieve the task successfully. So this angular momentum change is, I think, is completely generated by the momentum aware trajectory optimization without any manual hand tuning. So we also have the benchmark for two different structures. Like one is the kind of more hierarchical one, where the centroidal momentum kind of just send the information to the underlying whole body optimization in a single top-down direction. And basically by examining the residuals of these different reference tracking cases, we can clearly see that the alternating direction method actually outperform than the hierarchical one from all the reference like center of mass and effector and angular momentum tracking. And I think the reason is obvious that our method really use this alternating mechanism to achieve better consensus between centroidal and whole body dynamics. So I would like to maybe conclude this talk by maybe throwing out maybe two questions. And this is something we are actively developing these days. So first is literally about, okay, since this alternating direction method is very promising for better consensus, so can we really generalize it to more complex and large scale nonlinear program? And I think the answer is partially yes. And we have kind of recently generalized this approach to solve real-time MPC for manipulation with deformable contact. I will not talk about all the details, but literally we have 3 blocks, including whole body dynamics solved by DDP, inverse kinematics, and another block handle other states control constraints. But however, this is just a 7-DoF robot arm, which is actually not as complex as humanoid robots, although I think the deformable contact part is maybe have some complexities. But what about maybe more complex dynamics for the robots, such as this linear complementary constraint for contact and the high order under-actuated robotic systems? And how can we really achieve dynamic consensus in a very efficient way? I think currently many of this alternating direction method largely depends on the numerical convergence performance. But I think there may be more fundamental questions we need to address from the optimization algorithm structure design aspect, and what is the appropriate maybe this primal dual updating sequence for different blocks, and how can we really divide this entire problem into subproblems. I think there may be more fundamental optimization algorithm questions we need to address. And I think I just attended another workshop this morning, and I think Ludwig actually showed some very nice presentation on their approach to handle this problem in a very very fast way, and have very good solvers leveraging the good first order, second order gradient information. I think all of these questions kind of needs more scientific investigations in a principled way. So I'll be real quick. I think the second question is about this angular coordinates. So I think what is the appropriate representation for this angular coordinate at the centroidal level? And I think this question seems not very related to the distributed optimization architecture design, but it actually can potentially make a difference, how the centroidal information are processed in the specific blocks and passed through across maybe different centroidal and whole body blocks. So I only maybe have 1 or 2 more slides to go. I think there are really a lot of serious work exploring these directions, and I think people propose different angular representations, such as angular excursion, equimomental ellipsoid, and this maybe new angular central mass actually from HMC. I think there are a lot of works, and I think the angular excursion and ellipsoid, equimomental ellipsoids representations, it kind of have a lot of applications, but I think each of them have their kind of downsides, pros and cons. Well, I can talk this for maybe another 20 minutes, but I'll kind of skip some of the details. But I think I want to mention is that I think many existing locomotion tasks right now still try to kind of minimize the centroidal momentums, and it's not very clear how these angular representations can really work in highly agile bipedal, like maybe humanoid cases such as running, flipping, and especially those involving large angular momentum variations, like even using the swing arms. And this is some like very preliminary data we generate on our digits simulation, like this jumping and flipping with these dynamic arm movements. And I think we definitely don't have a clear answer which representation to use. So here, the blue ellipsoid represents these equimomental representations, while the yellow one denotes the angular recursion representation. And I think in these very initial observations, we can notice that this equimomental ellipsoid is kind of more aligned with the torso orientation, and the angular excursion ellipsoids kind of move to a specific configuration which have a little bit less physical intuition, especially at the end of the motion. So I mean, this is a very preliminary result. I think we should keep improving the motions. This is just solving like a single DDP problem. But I think this at least shows some like interesting directions and give some good insight. And this is also some like kind of special credits go to Patrick Vinson, kind of share some nice insights on this problem. And so with that, I would like to stop and thank my students, all the collaborators and the funding agencies, and thanks for your attention.
Thank you so much, Ria, for the interesting talk. So if you have any questions, please write in the chat or raise hand. If there is any question, Steve, in the audience, otherwise I can ask one I have.
Yeah, go ahead.
Okay, so yeah, you're basically, as far as I understood, you're saying that we should solve the problem, trajectory optimization problem, through whole body trajectory optimization and try to, you know, take advantage of the structure of the problem and so on. But anyway, the problem is non-convex, right? And when it's non-convex, it means that, you know, we have the local minima problem. So either we need a warm start or we need to do a lot of tuning and so on. At some point, we are losing the planning capability, right? Because we need another thing to plan for us. So what do you think about, so should we keep basically the simplified model at some point, such that through convex optimization, we can do planning, or you think, no, we should throw it away?
No, I think this is a very nice question. And actually, we face a lot of problems when we try to solve these alternating direction problems. And as you said, this problem is a highly non-convex, nonlinear program. And many times I mean, there are kind of a lot of numerical problems we have to deal with. But I think, or in terms of the models, yes, I think we should think about maybe both like a centroidal and whole body dynamics, but maybe for different blocks, for different tasks, we can look at them like kind of a little bit separately. But I think one like lessons we learned from our work presented today is literally we can not only look at like the centroidal informations. For some motions, we definitely, so for example, these zero gravity problems, we definitely need to use the robot's limbs to move around, and this definitely highlights the importance of the like whole body dynamics information. But how this whole body dynamics information is going to communicate with the centroidal information, I think this is kind of the thing we have to think about, and maybe from the optimization structure aspect. And I agree. I mean, right now this like trajectory optimization is only solved offline, so it's not really fast. And I think some of maybe your previous work and maybe Ludwig's program have this like QP solver. I just learned this morning, and it can really solve things very fast. So this is definitely some interesting direction we would like to take a look at further. But here we are still solving like planning problems. We are not solving for control, I guess. So yeah, but I think getting thing problems convexified, this is definitely interesting. But I don't have a clear picture whether we can convexify everything, and especially when the robot dynamics become more complex, the environments, the task become more complex, you might not have the capability to convex everything. So you still maybe have convex QP problem for some blocks, but some others we might not guarantee that. So it's still kind of a, I think, problem dependent, I guess.
Okay, thanks a lot. Robert, do you want to go ahead?
Yeah, so great talk. I enjoyed it. I always like seeing your work, so that's fantastic to see what you've done here recently. I was wondering if you could kind of explain, I may have missed it, but I don't really seem to understand how your LTL system interacts with kind of this controller behavior tree.
Yes. So this LTL is basically make this. So this LTL synthesize this reactive decisions at discrete level. So you can think for each walking step, it only make one decision for the apex, like that we call keyframe state. So you can think it's basically center of mass, apex velocity, and the foot locations. So this can only handle perturbations at this very specific time. But in the real physical world, the perturbations can actually happen at any time, right? During any locomotion phases. So this is something the LTL synthesis cannot handle properly. And then we propose the behavior tree at the lower level. So this behavior tree is, you can think it's kind of like a more advanced, like hierarchical finite state machine, actually used a lot in, I think, graphics and video games. But it's kind of very nice. They have very modular structure to make online modifications. So in this case, we leverage it to handle the perturbations that can happen at any continuous time. And in this case, we have like a strategy to handle perturbations at a very specific time. We have behavior tree can handle the perturbations at any continuous time. So overall, we can handle like both continuous and discrete perturbations. So I think this is kind of another layer we want to add into our framework, which can handle, I think, more realistic real-world perturbations. Does that kind of answer your question?
I think so, yeah. I'm interested to find out more, but that may be a little bit longer form conversation than what this medium is really good for. And I did just have one other question, which was how much crossover is Cassie actually capable of achieving with its steps? Because, you know, it looked like in your example video and where you had in the top right, it looked like one foot kind of went right in front of another, but it didn't really get like super far over as you would kind of expect of
Yes.
a, you know, natural or organic system. And, you know, I
Yes.
was wondering if that was something that if you're like hitting the hardware limits or if it was just kind of an artifact of this test.
Yes, so this one actually is not the, I think, I don't want to claim this is not the largest line crossing motion we can achieve. And I think this one probably roughly only 4 centimeters. I mean, the angle is not really the good one, I think, but you can see it's 4 centimeters. But I think when we did the experiment, we can achieve larger line crossing behaviors, like maybe reaching 8 or 10 centimeters. But it's definitely like hardware limits. We actually broke the leg once when we did this kind of experiments. Yeah, so especially this spring, you see the springs around the knee part of the
Okay.
is where the most collision actually happens. And so we are still trying to solve this problem. And this is kind of this kind of hierarchical problem, right? Like when we design, there are definitely low-level physical constraints from the trajectory optimization side, and how we can incorporate this real physical or kinematics constraints into the LTL high-level decision. So this is something right now we are doing in a little bit kind of empirical way, but we are kind of looking for more formal way to refine the high-level task specifications, which kind of taking into account the underlying robot physics and kinematics constraints. Yeah, this is actually a key question we are still trying to address.